Hello, we are Team 21005, and today we'll be presenting our project, which is the apparatus for measuring the thermal conductivity of return samples from Asteroid Bennu. Our sponsor is the University of Arizona's Lunar and Planetary Laboratory, and our point of contact is Dr. Andrew Ryan. My name is Sean Cherian, and I am studying mechanical engineering.
I'm Zane Craddock. I'm studying systems engineering, and I'm the team lead.
I'm Michael Gibson, and I'm a student in materials science and engineering.
I'm Aaron McCommon, and I'm studying systems engineering.
I'm Andrea Ochoa, and I'm studying electrical and computer engineering.
I'm Jinghua Ouyang, and I'm studying mechanical engineering. The goal of this project is to develop a new experimental apparatus for measuring the thermal conductivity of return samples from the near-Earth asteroid Bennu as part of NASA's OSIRIS-REx mission. During the early scientific studying, we have already known the sample will be tiny, fragile, porous, and irregularly shaped. The sample retrieved from the asteroid Bennu is precious and valuable in scientific research, especially in the formation and evolution of our solar system. We will be measuring thermal conductivity without destructed, contaminated, and altered sample in mineralogy and chemistry to maintain its most pristine state for other scientific analysis.
Here you can see our project requirements and the method with which they will and have been validated. You can see marked in blue provisional pass, meaning we expect this requirement to pass, and in green a pass, meaning we have validated in a nitrogen environment. Additionally, the requirements highlighted in orange require a vacuum chamber for validation. We've marked these with provisional passes, and LPL will need to verify these requirements inside of a vacuum environment after our team is done with this project. Additionally, important project requirements such as thermal conductivity accuracy and precision have not yet been verified. We will be performing tests for these requirements in a nitrogen environment in the coming weeks. Finally, the sample mass change and sample contamination requirements have not been marked with a pass since it's really necessary to test these inside of a vacuum environment.
The method that we decided on to measure the thermal conductivity of the sample involves heating an upper hemisphere while keeping a lower hemisphere held at a constant temperature. There will be a small gap between the two hemispheres, which will be where our sample mount plate will be located. Additionally, there will be a larger upper hemisphere that envelops the inner hemisphere, and they'll be heated at the same temperature to create an artificial insulation zone that will prevent radiation from going outwards from the inner top hemisphere to the outer. The system will be left on until it reaches a steady state temperature, which will then give us a thermal gradient through the sample. The thermal gradient affects the measured temperature of the upper hemisphere, which will be measurable by the RTDs that we have chosen. We will then create an ANSYS model that accurately simulates the experiment that we have conducted, and from ANSYS analysis we'll be able to determine the accurate thermal conductivity of the sample.
Here is the system block diagram of our system. The experiment control PC is able to control the temperature of several parts of the apparatus. The top hemisphere is controlled by PID1, the inner hemisphere is controlled by the power supply, and the cold plate is controlled by the PID2. These work in conjunction with one another to establish a thermal gradient across the sample. Resistance temperature detectors collect temperature data at various locations that is then sent back to the PC via data acquisition system. The apparatus, sensors, and heaters are designed to work inside a vacuum environment. The system architecture shows how each subsystem is defined. The thermal subsystem consists of PIDs and the precision power supply. The data subsystem is a DAQ. The control subsystem is the PC and LabVIEW. Then the mechanical subsystem consists of the main apparatus, the RTDs, and the heaters.
Here is a sample of some various simulations that we have performed. We developed an error budget for various components on our apparatus, and we also used DOE to organize our experiments. The error budget analyzed how the thermal conductivity changes when compared to the temperature of the top hemisphere. We also analyzed the effect of changing the radius of the top hemisphere compared to the temperature of it. From this, we were able to calculate a variety of tolerances for different error sources in our apparatus design. Currently, to obtain an accuracy of plus or minus 5%, we need to know the radius of the inner hemisphere within 0.01 millimeters. This error analysis helps us determine which variables we need to have a higher accuracy with, and which variables our tolerances are less important. The design of experiments method that we followed helped us organize our ANSYS simulations in files with easy to understand results. We were able to conduct analyses with these methods and extract results from this that helped us determine important factors in the experimental design. We also did linear regression on our results to see which parameters had the largest effect on our design. From this, we see that the heat flux magnitude and emissivity of the sample and shell have the largest effect on our design.
Here you can see an exploded view of our finalized SolidWorks mechanical design. The design itself consists of 7 different parts. Starting from the top and working our way down, we begin with the outer top hemisphere and the inner top hemisphere. Both of these aluminum machined parts serve as the heat source for the sample. Having 2 separate hemispheres allows for minimal external heat loss by setting the temperature of the outer top hemisphere to match the temperature of the inner top hemisphere. Next we have the sample itself, which rests on a set of threads made from Teflon. This threading is then attached to the sample mount plate, which is machined out of Teflon and additionally serves as the middleman between the 2 sets of hemispheres. Additionally, this sample mount plate allows for the sample to be placed near the center of the 2 sets of hemispheres. Speaking of which, the bottom hemisphere, which is machined out of aluminum, is carved out of a cylindrical base plate and acts as the heat sink. The 7th component, which is not shown here, is the copper base plate located within the vacuum chamber, which is what the previously mentioned components rest on top of. Due to the number of electrical components present in this design, it was necessary to organize everything through the use of a wiring diagram. Here in this diagram, you can see the intricacies involved with this project. To begin, there is an experimental control computer which, through the use of LabVIEW, operates the PID controller, data acquisition unit, and the power supply. These components are used with a set of resistance temperature detectors located throughout the apparatus to accurately record temperature. Additionally, the power supply is used to provide power to 32-gauge resistance wires, which are wrapped around both the inner and outer top hemispheres as their heating elements. All the information gathered from these sensors and heating elements is then fed back to the experimental control computer and consistently monitored to determine when a steady-state solution has been achieved. Due to time constraints, it was found that a larger number of experiments could be ran if they were performed outside of the vacuum chamber. This is because the time required to evacuate the air within the vacuum chamber and to bring the pressure down to the desired level would be eliminated. To mimic the vacuum environment, a nitrogen box was constructed from plastic sheets and PVC piping so that nitrogen gas could be pumped into the chamber, allowing for the humidity level to be as low as possible, which was measured through the use of a hygrometer. Additionally, since the vacuum chamber was not being used, this means that the copper plate would not be available for testing. To recreate this, a set of copper plates placed on top of a styrofoam container containing liquid nitrogen was used as the vacuum plate, with a capped-on heater placed in between them. This capped-on heater was then attached to a second PID, which allowed for the copper base plate to reach the desired temperature necessary for the experiment.
This project has faced a few challenges, from switching suppliers last minute to redesigning your apparatus 3 significant times after months of research. The design process took most of our time to finalize a design that would be able to fulfill our given project requirements. The process of ordering parts and assembling the apparatus took longer than what was originally expected. Most recently, we received an incorrect part, and as a team, we came together with a list of contingency plans that led to a quick resolution, and we received a new incorrect piece within a week of the mistake. We faced a new challenge of filing a descope on our project due to some scheduling issues, but with the help of our sponsor, we navigated a plan that worked for both parties. We did not change any requirements for the project as a whole, just simply adapted the schedule of work to reflect what could be done by our team within our timeline and what could be done after our scope of work is completed. As for deliverables, our apparatus is ready for validation inside the vacuum environment, the scope of the project that we were able to achieve within our design timeline. The apparatus, along with the final report and our operation manual, will be delivered to our sponsor at the end of the design timeline.